So if you're listening to this, you're probably seeing the same headlines we are. Like, everyone is obsessing over these multi-million-dollar data centers, right? Training the next massive AI model.
Yeah, completely. It's all about the sheer scale of the data. The huge server farms, the electricity they burn through, just to make a neural network smart.
Right. But, I mean, they are completely missing the real story here. Because training an AI is fundamentally, it's just a money pit. It's a pure cost center.
Exactly, it's just burning cash.
Yeah. The people who are actually getting filthy rich in AI right now, they're doing something incredibly boring.
Well, boring to the outside world, maybe. But they're working on inference, which is, taking that massive, super expensive trained model and actually serving it to millions of users out in the real world.
Right, because without inference, a trained AI model is just, it's basically just a giant, useless file taking up space on a hard drive.
Yeah.
I mean, you can't just sell a CD-ROM with a language model on it and call it a business anymore.
Yeah, no, those days are long gone. You have to build a system around it that can handle this relentless barrage of queries, and you have to do it at scale without bankrupting the company.
Which is wild. And that turns out to be this fascinating, brutally complex engineering challenge, right?
Oh, absolutely. You are literally fighting physics, you're fighting hardware limitations and software bottlenecks all at the exact same time. It's chaotic.
And that is exactly our mission for you today. We are taking you on a deep dive through this amazing Stanford University masterclass, which was led by a guest lecturer named Charles from the serverless computing company Modal.
Yeah, it's such a great source. We are diving into the absolute trenches of serving large language models here.
Right, we're going to unpack the hardware bottlenecks, the software hacks, and just the sheer engineering effort required to keep AI running at scale. Okay, let's unpack this.
So before we can even begin to talk about the physical servers, we really have to understand the specific type of work the AI is being asked to do, because you can categorize LLM applications into 3 distinct archetypes, and they place completely different demands on the infrastructure.
Yeah, I like to think of this like a restaurant kitchen,
Yeah.
So the first archetype is Chatbot Plus. Think of ChatGPT or Claude. This is like the fast food drive-through window of AI.
That's a great way to look at it.
Right, because there's a human being sitting there, staring at a screen, waiting for their answer. Speed is absolutely everything. They are highly sensitive to interactive latency, basically just sitting there waiting for every single token or, every word to appear on the screen.
Yeah, and because of that human element, the critical metric there is interactivity. So engineers measure that in tokens per second per user. It is a super high-pressure environment for the hardware.
Totally.
Then you have the second archetype, which is background agents. These are those autonomous coding systems like Devin or SWE agent.
Right, so keeping with the kitchen analogy, this is like ordering a slow-cooked roast. You give the agent a prompt to go write like a complex pull request or maybe design a whole software architecture document.
Exactly.
And you are sitting on the edge of your seat watching it type code line by line. I mean, you go to a meeting, you grab a coffee. The latency constraints here aren't measured in milliseconds. They stretch into minutes or even hours.
Which is huge because that completely changes how you schedule the computing power. You can batch these requests together in much, much more efficient ways.
Right, you have breathing room.
Yeah. And then the final archetype is data processors. This is the bulk extraction of structured data from unstructured text.
Okay, so the bulk catering order.
Exactly. For instance, the source mentions a system called Reducto that was used to process that massive dump of Jeffrey Epstein emails.
Right, which is just an example of a huge data ingestion task.
Yeah, exactly. The goal there is just to ingest a mountain of unstructured PDF and text files and turn it into a cleanly searchable database. You aren't worried about interactivity at all.
Right, you don't care how fast the very first plate of food comes out of the kitchen. You just care about the total volume of food produced per dollar.
Spot on. So for data processors, the metric that matters is throughput specifically, megatokens per dollar. And engineers measure all of this using 2 critical metrics: TTFT, which is time to first token, and TPOT, time per output token.
Time to first token and time per output token.
Got it.
So how long until the AI starts talking, and how fast does it spit out each subsequent word?
You got it. But what's really wild is that you can't just look at this for your entire system globally. You have to reason about these workloads per replica.
Wait, per replica, meaning like on one single instance of your model running on one GPU.
Yeah, exactly. A single replica has a hard physical limit on how many concurrent queries it can handle before it just busts its latency budget. If you cram too many users onto one GPU, the time per output token skyrockets.
Then everyone's chatbot starts stuttering.
Exactly. You also have to factor in prefix reuse. Like if multiple users are sending prompts that share the same underlying system instructions or maybe the same large document context, a smart inference engine can actually cache those previous computations.
Oh, wow. So it essentially takes what would be this massively expensive math problem for the graphics card and just turns it into a cheap, simple data retrieval from storage.
Yeah, it's a huge optimization. So once you map out your application, whether it's the fast food, the slow roast, or the bulk catering, you have to select the engine, the model itself.
Right, because the application dictates two entirely different engineering philosophies or like regimes for how you deploy.
Yes. The first is the efficiency-bound regime.
Yeah.
This is where the baseline intelligence of current models is already, good enough for the task at hand.
Yeah, I mean, if you just need a model to reformat a huge spreadsheet of dates,
Yeah.
you don't need a massive supercomputer to do that.
Exactly. The goal here is purely driving down costs. So this regime is completely dominated by open source models, systems like Qwen, Mistral, or Llama, and they usually run super efficiently on single GPU setups.
I think it helps to think about this like monitor refresh rates. Like once you buy a computer monitor that hits 100 hertz, it looks perfectly smooth to the human eye. It's totally fine. Very few people actually need a 1000 hertz monitor.
Right, the problem is solved.
Yeah, so you just look for the cheapest 100 hertz screen you can find.
Exactly. But then you encounter the second regime, which is capability bound. This is for tasks that demand the absolute bleeding edge of machine intelligence. Cost basically takes a total backseat here because the problem is so difficult.
You are just throwing everything you have at it.
Everything.
So capability bound is more like computer RAM. Like Google Chrome always wants more RAM, and we never, ever have enough. You will always just buy more if you can afford it.
That's a perfect analogy. And these setups require massive multi-node, multi-GPU orchestration. Historically, this territory has been entirely dominated by proprietary providers.
Right, the big tech companies.
Yeah, but what is shifting rapidly right now is that open source fine-tunes models like DeepSeek v4 are starting to really blur this line. They're catching up to proprietary capabilities while still maintaining that lean efficiency of open source architectures.
Okay, so we know the task and we know the model regime. But when we actually try to run this software on physical hardware, we run headfirst into a massive wall of physics.
Oh yeah, the memory wall. This is where the reality of inference engineering becomes incredibly hostile.
Hostile is a good word for it.
Yeah, because generating an AI response happens in two distinct phases, prefill and decode.
Right, so prefill is when the AI processes your initial prompt.
Yeah.
Like if you paste a 10-page PDF document into a chat window, the GPU has to crunch all of that text at once to just understand the context.
Exactly. And during this phase, it is using up all the arithmetic bandwidth of the GPU. It's doing a mountain of heavy math simultaneously.
Okay, so that's prefill.
Yeah. But then we ship to the decode phase. This is when the AI actually starts generating the output tokens, one single word at a time. And for every single token it generates, the system has to load all of the model's weights, which, by the way, can be 70 or 80 gigabytes of data from the GPU's high bandwidth memory directly into its processing registers.
Wait, for every single word?
For every single...
So if it generates a 100-word sentence, it is physically moving those 80 gigabytes 100 separate times.
Yes, that is the bottleneck. During decode, the GPU is only performing about 2 or 3 floating point math operations for every byte of data it loads. It is heavily memory bandwidth bound.
Wow.
Yeah, the massive math processors on the chip are basically just sitting there, twiddling their thumbs, waiting for the data to physically travel from the memory banks to the processor.
Okay, but wait. If memory bandwidth is this massive bottleneck, why are we all fighting over these impossible-to-find NVIDIA chips? Like, why can't I just buy a farm of cheap standard Intel CPUs and brute force the memory problem?
Because traditional CPUs simply lack the tightly integrated architecture required to move that much data that fast. They just don't have high bandwidth memory stacked directly next to the compute cores. And they lack the granular L1 cache control needed to shuffle gigabytes of weights efficiently.
Wow, I see.
Yeah, so you absolutely need specialized data center GPUs. Specifically, you need GPUs with an SXM form factor.
Which is very different from like the standard PCIe graphics card that someone might plug into a desktop gaming motherboard, right?
Completely different. An SXM module isn't a card you slide into a slot. It is literally bolted directly to the motherboard with these massive copper heat sinks.
Whoa.
Yeah, and this allows data centers to pump hundreds and hundreds of watts of power straight into the chip without melting the server. You need that sheer wattage to push the memory bandwidth to its absolute physical limits.
That is insane. And because these hardware constraints are so bizarre, developers can't just run these models using standard Python web scripts. I mean, they have to use these highly specialized inference engines just to manage the memory.
Yeah, and what's fascinating here is the culture of these inference engines. You have this massive split in the open source community trying to solve this memory wall. On one hand, you have VLLM.
Right.
It has a very enterprise Linux Foundation vibe to it. It's stable, it's widely adopted, and it's carefully managed by committees.
And then on the other hand, you have SGLang,
Yeah.
which has this high-speed, chaotic, gotta-go-fast startup energy. Like, there are dozens of hyper-optimized branches of SGLang just floating around the internet with absurd, highly specific little hacky optimizations baked into them.
Exactly. It perfectly illustrates the desperation engineers feel trying to squeeze every last drop of performance out of the hardware. Because honestly, the hardware itself is incredibly brittle.
Yeah.
Understanding the memory wall is one thing, but keeping a massive fleet of these SXM GPUs alive in the real world is a completely different nightmare.
Because these models require gigabytes of high-bandwidth memory just to generate a single word, you need massive GPU clusters. But here's the brutal reality of running those clusters in the wild. They break constantly. Yeah, like if you are used to traditional web servers, you expect them to run quietly in a server rack for years. But NVIDIA H100 GPUs fail. Often. Their mean time between failures, or their MTBF, is measured in weeks or even days.
It's highly reminiscent of the early days of computing with, like, spinning hard drives. Hardware failure isn't an anomaly here, it is a baseline assumption. You have to build immense redundancy into your systems, just assuming a certain percentage of your multi-million-dollar hardware will simply die on any given Tuesday.
Which is a terrifying way to run a business.
Yeah.
But beyond the hardware just dying, the biggest headache for deployment is traffic spikes.
Right.
AI usage is incredibly bursty.
Oh, yeah.
You might launch a new feature, go viral on Hacker News, and suddenly have 10,000 users hitting your model at the exact same second.
And you can't just boot up an inference server on demand like a regular web app, because just loading 80 gigabytes of model weights from storage into the GPU memory takes minutes.
By the time the server actually boots up and is ready to answer a question, the user has closed the tab and left.
Exactly. So infrastructure engineers have had to invent these incredibly clever serverless techniques to survive these traffic spikes. They do things like lazily loading the file system.
Lazy loading. How does that work here?
So they basically trick the GPU into thinking the entire model file is already present while they are actually streaming chunks of it in the background just in time.
That is so smart.
Yeah. And they also use eager fetching for the core PyTorch libraries. PyTorch is essentially like the mathematical nervous system the model runs on. By fetching those underlying libraries from cloud caches before the server is even fully active, they keep a pool of idle GPUs semi-warm.
Right, so the goal is to allow a dormant server to instantly join the fight the second a massive traffic spike hits.
Precisely. It's a highly complex shell game with multi-million-dollar hardware.
So what does this all mean when things inevitably break? Because they do. And the debugging process here is totally alien to normal software development. I mean, let's talk about tokenizers, because the engineers in this space consider them deeply cursed.
Curse is the exact right. So tokenizers are the systems that translate human text-like letters and spaces into the specific numbers or token IDs that the AI actually understands.
Right. And if an engineer is trying to fix a broken model, the prevailing wisdom is that they must log the raw token IDs, the actual numbers, instead of just the text strings the user typed. Why go to that level of abstraction?
Because text strings lie to human eyes. I mean, a string of text might look perfectly normal to a developer staring at a log file, but hidden inside that text are often subtle Unicode bugs.
Oh, like what kind of bugs?
Things like hidden zero-width spaces, bizarre formatting artifacts, or maybe mixed language characters that look identical to English letters. The tokenizer interprets those invisible glitches in catastrophic ways. It translates them into bizarre number sequences that cause the model to completely hallucinate.
Wow.
Yeah, so if you only log the English text, you will literally never see the bug. You have to log the raw numbers to see exactly what broken sequence the model was fed.
That level of microscopic debugging is intense, and it really raises an important question about how we even measure if a system is working well. Like in observability, looking at P50 latency, meaning the median response time, is basically a lie.
It really is. Your median response time might look blazingly fast. 50% of your users are getting a great experience, but you have to look at the P99 tail latencies.
The worst 1% of requests.
Yes, because in traditional software, a slow request just means a loading spinner spins a bit longer. But in AI, a slow request means stuttering token generation.
Right, so the model pauses for 2 seconds in the middle of a sentence, and it completely ruins the illusion of intelligence for the user.
Exactly. And that stuttering is usually caused by hidden queues buried deep in the infrastructure. It's basically a traffic jam inside the server where requests are piling up, just waiting for a tiny slice of memory bandwidth.
Which brings us to the hacks. Since GPUs fail constantly, traffic is unpredictable, and the memory bandwidth is severely bottlenecked, engineers are basically forced to invent ways to cheat physics to get faster outputs.
Yeah, cheating physics is the job description. And the first huge lever engineers use to cheat time is called speculative decoding.
Okay.
So, think back to the decode phase we discussed earlier. The GPU is starved for memory bandwidth while it loads the weights, but its massive compute processors are basically sitting idle. Speculative decoding puts those idle processors to work.
Okay, let's bring in an analogy for this one. Imagine you have a brilliant, highly paid, but totally overworked senior editor. That is your big, expensive AI model.
Right.
And you hire a speedy, slightly less accurate junior writer to sit right next to them. That's a tiny, highly efficient draft model. Since the big model is going to take forever to type out the response word by word anyway, you have the junior writer instantly draft the next 5 words.
Exactly. And then you hand those 5 drafted words to the senior editor. The big model can verify all 5 words at once in a single, massive parallel computation.
Because the math processors were sitting idle anyway.
Yes. So verifying 5 words takes almost no extra time compared to generating 1 word from scratch.
That makes so much sense. So if the junior writer guessed right, the editor approves the whole chunk instantly. If the junior writer got word number 4 wrong, the editor accepts the first 3, deletes the rest, and just corrects word 4.
Which yields massive speedups. We are talking 2 to 6 times faster generation times here. And the engineering behind the draft models is getting incredibly sophisticated. Like, there is a project called Delash, which uses diffusion language models.
Wait, like the technology that generates AI images?
Maybe similar, yeah. But applied to text to generate these highly accurate drafts almost instantaneously.
It's just brilliant. Like, instead of trying to make the car drive faster, you just pave the road ahead of it while it's driving.
That's exactly what it is. And then the second massive lever for cheating physics is quantization. This is the act of shrinking the precision of the numbers the AI uses to do its math.
So we are talking about compressing the literal size of the data.
Yeah. Historically, models used 8-bit floating point numbers, or FP8, but engineers realized that you can often compress those down to FP4 or 4-bit numbers. And because the numbers are literally half the physical size in the computer's memory, it instantly halves the memory bandwidth requirement.
Oh, wow. You're moving half as much weight, so it moves twice as fast.
Yes, it offers linear speedups. It is the most direct way to attack the memory wall. Now, obviously, shrinking the precision restricts the mathematical vocabulary the model has to work with.
Right.
So it carries a risk of degrading the model's reasoning performance, particularly on very long sequences of text where tiny mathematical rounding errors kind of compound over time. But for many applications, the speed trade-off is absolutely worth it.
And this highlights a crucial lesson for engineers working in this space, right? Do not get distracted by the tiny stuff. It is really tempting to dive deep into kernel optimizations, like using advanced profiling tools like Nsight Compute to chase a fraction of a millisecond on a single math operation.
Oh, premature optimization is a total trap here. The true engineering wins don't happen at the micro level. They happen with big architectural shifts, like implementing speculative decoding to draft tokens or aggressively utilizing quantization to halve your memory footprint.
Right.
Only once you have completely exhausted those massive levers should you even consider getting out a whiteboard and writing custom GPU kernels.
Man, we have covered an immense amount of ground today. We started with the business reality. how Inference is the actual engine turning AI from a research project into a real economy. We broke down how the latency needs of chatbots differ entirely from the bulk processing of background agents.
We explored the brutal realities of the memory wall, the physical architecture of SXM modules, and all those serverless hacks required to survive bursty traffic and constant hardware failures.
And we wrapped up with the sheer ingenuity of speculative decoding and quantization. But, as we finish up this deep dive into the Stanford material, there is a lingering idea to mull over here.
Yeah.
Throughout this entire exploration, we've been talking about the human engineers. The people logging the raw token IDs, managing the server cold starts, configuring the memory caches, the people getting filthy rich right now holding this infrastructure together.
But the explicit goal of the broader AI industry is to create systems capable of doing complex reasoning and coding tasks. So the future of software engineering inevitably includes AI agents actively participating in the engineering process.
Which fundamentally shifts the human role. Instead of humans doing the optimization, humans will just build the systems that allow AI agents to measure, benchmark, and rewrite the code themselves.
It is the ultimate paradox of the field right now.
Yeah. If the future involves AI agents actively writing code, configuring monitoring tools, and optimizing serverless infrastructure. Wait, what happens when these models become the primary engineers optimizing their own inference engines?
Yeah, will the boring infra jobs that are so incredibly lucrative today eventually be completely automated away by the very AI they are currently trying so hard to serve?
It's like you are building the machine that might ultimately figure out how to run itself better than you ever could.
Exactly.
It really makes you wonder if getting filthy rich on boring infra is a permanent career path or just a very, very lucrative temporary window in history. Well, thank you for joining us as we unpack the true mechanics of how AI actually reaches the world. We'll catch you next time.